Okay friends, today we are going to discuss about linear programming problem, that is LPP. You are well versed with linear equation and linear inequation in 1 and 2 variables, and also we have discussed in details how to solve system of linear inequation in 1 variable and 2 variables, algebraically and graphically. Now we discuss about how to use the concept of linear equation and linear inequation in 2 variable in the field of linear programming problem. So linear programming is nothing but the process of optimization. So in day-to-day life we have to deal with various problems that needs optimization, or we have to find its maximum value or minimum value. So linear programming problem is one of the process of mathematical optimization process. So we can say linear programming, also called linear optimization, is a method to use to achieve the best outcomes such as maximum profit or lowest cost. These are examples in a mathematical model whose requirements are represented by linear relationship. It is special case of mathematical optimization. Let us take some example from day-to-day life situation or from real world. So in a military operation, the military effort to inflict maximum damage to enemy and minimum loss. In an industry, manager wants to maximize profit under the constant manpower, capitals and available resources. Similarly, a salaried class person wants his saved money for investment to maximize his profit under minimum tax liability. Similarly, we have many examples like transportation problem. Say there are 2 factory P and Q and 3 warehouses, and this factory P produce 5 unit and factory Q produce 6 unit, and the warehouse A has capacity to accommodate 4 items, and warehouse B has capacity to accommodate 4 and C has capacity to accommodate 3. Now from P to A, from P to B and from P to C, we have to transport the goods that produce from factory P and Q, and purpose is to minimize the transportation cost, and transportation cost is there. From P to A is given, from P to B is given, from P to C is given, from Q to A, from Q to B, from Q to C. So what will be the quantity that will be sent from P to A, P to B, P to C, similarly from Q to A, Q to B, Q to C, so that the transportation cost will be minimum. So we have many such type of problems. So before going to discuss this problem, we have to discuss in details about LPP, means linear programming problem. So linear programming problem has two parts. First part, that is constants are represented as linear equation or linear inequation. And this may be of one variable, two variable, or more than two variable. And second part is plan of action. Plan of action. This part is called programming. And 1 and 2 together is called linear programming. So we have two actions. First of all, we have to define all the constants in linear equation or linear equation that may be of one, two or more than two variable. And second is how to plan so that we have to maximize or minimize the linear function or objective function. So we can say linear programming is a method for determining optimum value of a linear function subject to constants as linear equation or inequation. Some definition, that is objective function, the decision variables, constants, optimization problem, feasible region and feasible solution. So first of all, we have to discuss these 5-6 technical terms. Objective function a linear function z equal to ax plus by, where a, b are constant. Is called objective function which have to be maximized or minimized. So first of all, we have to define objective function. Then second is decision variable. X and Y are called decision variable X is always greater than equal to 0 and y is always greater than equal to 0, means x and y have non-negative restriction. Means x and y is never negative. Then third is constants. Constants means condition. Or we can also say hurdles that we have to face when we have to maximize or minimize the objective function. So it may be linear equation in the form of linear equation, linear inequation, and condition on decision variable. Variables. Now fourth point is optimization problem. Optimization problem. A problem which seeks to maximize or minimize is called optimization problem, and this problem maximize or minimize under certain constants or condition. For example, suppose in industry, if a industrialist wants to maximize his profit, then the constants may be number of manpower, available resources, and available capitals. So these are constants for industrial problem. Now, feasible reason. Suppose when you draw a graph of constants say and for these two constants, the defined region or common region for these two constants is, say, this shaded region, say OA BC. Then this OA BC is called feasible region satisfied by given constants, and this region may be bounded region or may be unbounded region. So, suppose if you draw a graph of given constants, and the common region for given constant is like this, then this is called unbounded region, and this feasible region is unbounded. This is unbounded feasible region. And all the points in this feasible region is called feasible solution. So, feasible solution alpha beta belongs to feasible region, then alpha beta is called feasible solution. Feasible solution for the given constants simultaneously. So these are some terms that we have to use during the course of discussion. Every feasible region, very important point, every feasible region must be convex set. So every feasible region must be convex set. It means, suppose you consider these are some different types of regions. So these are some different regions, and say the defined region are this. These are defined region. Let us consider 2 points, say one point is here and one point is here. Join these 2 points. Again one point is here and one point is here. Join these 2 points. Take any these 2 points in this region. Again 2 points in this region. So, figure 1, this is figure 2, this is figure 3, figure 4, figure 5. So, in all these 5 figures, only 3, 4, 5 are feasible region, because convex set means if you take any 2 points in the region and if you join that 2 points, the each and every points on the on the line must belongs to that region. So, in figure 1 and 2, these points doesn't belongs to the defined region. That's why figure 1 and 2 is not convex set, whereas figure 3 and 4, 5 are convex set. So, we have to consider only figure like 3, 4 and 5 during discussion. Now, graphical method of solving of linear programming problem. So, before we start solving of linear programming problem, we have 2 important theorems, or you can say 2 very fundamental theorems. Theorem 1 says that let R be the feasible region for an LPP and Z equal to AX plus BY be the objective function when Z has an optimal value, that is maximum and minimum, subject to the constants described by linear inequalities. This optimal value must occur at a corner point of the feasible region. So, in this region, these are corner points. These are called corner points, means vertex of the feasible region are called corner points. These are called corner points. And theorem 2 says that let R be the feasible region for an LPP and Z equal to X plus BY be the objective function. If R is a bounded, then the objective function Z has both a maximum and minimum value on R, and each of these occurs at a corner point of R. Remark, if R is unbounded, then a maximum or a minimum value of the objective function may not exist. If it exists, it must occur at corner point of R. So, let us discuss this theorem on a diagram. So, again consider 2 constants like this and 1 constant, say this, and if this constant define this half plane and this constants define this half plane and this constant define this half plane. So, common region for all these constants will be this, and this feasible region is a bounded region, and these points are called corner points. So, theorem 1 says that every feasible region have its corner points and its optimal value lies at corner points. And theorem 2 says that the optimal value, that is, if region is bounded, if this region is bounded, then this region must have both maximum and minimum value. Let us consider another region which is defined by different constants and say this is like this, and the common region for both the constants is this, and the corner points for this region is say ABC. So, theorem first said that whether region is bounded or unbounded must have corner points and its optimal values lies at corner points. But theorem 2 says if region is bounded, then both maximum and minimum value lies at corner points, and if region is unbounded, then there may chance of no maximum and minimum value, and if it exists, then it must exist at corner points. Now, corner point of a feasible region is a point in the region which is the intersection of two boundary lines, and bounded region can be defined as a feasible region of a system of linear inequalities is said to be bounded if it can be enclosed within a circle, otherwise it is called unbounded. Now, corner point method. So, to solve LPP, we have two very important methods, that is, first is simplex method and second is corner point method. Simplex method is useful when the number of variable is more than 2, and corner point method is very much convenient when the number of variable is very less, means 1 or 2. So, we discuss only here corner point method. Steps of corner point method. Find the feasible region of the LPP and determine its corner points either by inspection or by solving the two equations of the lines. What does it mean? Step 1 says that by plotting the graph of given inequalities, we have to define feasible region. So, whether that region may be closed region or may be open region. And steps 1 also says that by defining feasible region, we have to find corner point. If this will be the region, then this will be the corner points, and if this will be the region, then these three will be the corner points. So, step 1 says that first of all we have to plot the graph of all the constants and define feasible region and define its corner points. Now, step 2, evaluate z equal to x plus by at each corner point. Let m and m respectively denote the largest and smallest values. So, suppose z equal to, that is objective function z equal to x plus by, and if the feasible region have its corner point say A, B, C, then we have to find the value of z at A, means ZA, value of z at B, ZB, and value of z at C, that is ZC. Since the region is bounded region, so we must have among these three value, one value is smallest value and one value is largest value. So among ZA, ZB and ZC, one value must be smallest value and one value must be largest value. So according to step 2, we have to evaluate Z equal to X plus B at each corner point. Let M and M respectively denote the largest and smallest value. Now third step, when the feasible region is bounded, M and M are the maximum and minimum value of Z. So it means the smallest value will be the minimum value and largest value will be the maximum value when region is bounded region. This region is bounded region. And in case the feasible region is unbounded, say region is unbounded, then corner points of this region A, B, C say the value of Z equal to Ax plus By. So the value of Z at A is equal to say P and value of Z at B is equal to say Q and value of Z at C equal to say R. And if this P is smallest value and say R is largest value. Feasible region is unbounded, and if M is the maximum value of Z, if the open half plane determined by Ax plus By greater than M has no point in the common with the feasible region, otherwise Z has no maximum value. It says that if this ZC equal to R is maximum, then Ax plus By greater than R have no point in common with the feasible region if Ax plus By greater than R have no point in common with feasible region, then R is the maximum value. That is Z max equal to R at C. And if Ax plus By greater than R have common points with feasible reason, then z equal to x plus by have no maximum value. It means it says that our graph is like this, and this will be the open feasible region, and ax plus by draw ax plus by equal to r and if this ax plus by equal to r have no any common points with this feasible region, then this r means zc equal to r, this r will be the maximum value. I think it is clear. If this ax plus by equal to r will pass if this ax plus by equal to r will passing like this. If ax plus by equal to r is like this, then different points on these points which are common to this feasible region, then this r is not the maximum value of objective function. Similarly, in case of when m is minimum value, so za equal to p smallest value, and if this p is minimum value, then again ax plus by less than ax plus by less than p have no any common points with the feasible region, and if such condition holds, then we can say z at a equal to p will be the minimum value, and if ax plus by less than p have common value, with feasible reason, then za equal to p will not be the minimum value, or we can say minimum value doesn't exist. Now let us consider one example. Solve the LPP graphically. maximize z equal to 4x plus y subject to the constants x plus y less than equal to 50, 3x plus y less than equal to 90, x greater than equal to 0, y greater than equal to 0. Now first of all, define the feasible reason for the given constant x plus y less than equal to 50, 3x plus y less than equal to 90. Solution. Associated equation x plus y equal to 50, 3x plus y equal to 90. Say this is first and this is second and this is third. So x plus y equal to 50. So from 1, x plus y equal to 50, put y equal to 0, implies x equal to 50, x equal to 0 implies y equal to 50. So points on x plus y equal to 50 are (50, 0) and 0, 50. From 2, 3x plus y equal to 90, put y equal to 0, x equal to 30, x equal to 0 implies y equal to 90. So points on line 3x plus y equal to 90 are 30, 0 and 0, 90. Now draw the graph of these two lines. This is y-axis, 0, x-axis. So point is 50, 0 and 0, 50, 50, 0 and 0, 50. So each division will be of 10. So we have 2 points 0, 50 and 50, 0. Join these 2 points. So this is the line x plus y equal to 50. Now for second associated equation, points are 30, 0 and 0, 90. So this is 1.30 and this is 1.090. So join these 2 points. So this is equation of line 3x plus y equal to 90. So this line represents this equation 3x plus y equal to 90. Now x plus y less than equal to 50. So if you test origin test, the defined region, this line will represent this half plane, and second constant is 3x plus y less than equal to 90. So again origin test means zero plus 0 equal to 0 is less than 50. So this is true. Similarly, 3 into 0 plus 0 equal to 0 less than 90. This is again true. So in both constants, origin includes in the solution region. So again the solution region for this constant is in this direction. Now the decision variables x and y have non-negative restriction, so the region must define in first quadrant only. This is x greater than equal to 0 and this is y greater than equal to 0. So when you consider all these conditions, we will find this will be the feasible solution region. This will be the solution region. Now question is, we have to maximize z equal to 4x plus y. So these 4 points are corner points. So by inspection we see that the corner points are A 30 0, B 20 30 and C 0 50, and one corner point is origin. So corner points are 0 0, A 30 0, B 20 30 and C 0 50. So value of z at corner points z0 equal to 0, za equal to 4 into 30 plus 0 means 120, zb equal to 4 into 20 plus 30 110, and zc equal to 4 into 0 plus 50 equal to 50. Now in problem we have given maximize z equal to 4x plus y. So this will the largest value. Since feasible region is bounded region, so Z max equal to 120 at A 30. Okay friends, we discuss some more problem in next session. Thank you.